Our last lecture was devoted to distribution of Gaussian random vectors. Finally, we get the following relationship. If Gaussian random vector in the space RD has a distribution with mean M and covariance matrix A, then we already know that its characteristic function phi psi lambda is equal to expectation of the scalar product lambda psi is described by the formula So the distribution of Gaussian random vector is completely defined by its mean and covariance, exactly as it was in the one-dimensional case. Moreover, covariance matrix must be self-adjoint and non-negative, definite, and if determinant of A is greater than 0, then psi has density, and this density has the following form. Multiply on the exponent minus 1/2, and here is quadratic form of the inverse matrix to A. So in this case, we have density. In opposite case, when determinant is equal to 0, we already know that distribution of psi is concentrated on the subspace, which is equal to n plus A from RD. Actually, in our considerations, we started with A in 1/2 power, but it is the image will be the same due to the final dimension of RD. So one can see that in this case, this Gaussian distribution is concentrated on the affine subspace with the dimension which is strictly less than D. So it is concentrated on the set of zero measure, initial measure in RD, so it has no density. This was the end. This was the end of our considerations in the previous lecture. And today we have all tools to begin with the so-called Gaussian calculus in finite dimensional case. So let us start from some useful expectations, calculations in this case. let me recall you that we call Gaussian vector with the parameters 0 and identity matrix by the standard Gaussian vector. Our idea today, maybe the next lecture, is the following. We will consider random variables alpha, which are measured with respect to xi, and then due to the well-known fact from the probability theory, alpha can be represented as a function f from xi. And somebody can expect good properties of random variables alpha, properties of alpha must be related to properties of f. Namely, one can ask when alpha has density, what is the properties of the density? Is it smooth or not? And it occurs that such kind of smoothness of alpha can be related to the smoothness of the function f. Moreover, when discussing smoothness of the function f, so in usual sense, existence of derivatives of this function f, we will be able to represent this random variable as a series from some orthogonal summands, and we will discuss existence of the stochastic derivatives of the derivatives of f exactly in the same way as we discussed the existence of the derivatives of the function which is represented by the trigonometric series. This is our plan, but we will start from some concrete calculations related to this standard Gaussian vector. Let us introduce the following function. For any h which belongs to our Rg, define the following random variable. E of h will be equal to exponent of product h psi minus 1/2 of the norm of h squared. You see, this is a random variable of such kind, and it occurs that we have some very nice properties of these random variables. Firstly, let us take the expectation of this random variable. I will write this expectation using the fact that our xi has standard normal distribution, so it has density, and we can calculate the expectation using density of this standard Gaussian distribution. We will get the following expression. It is integral with respect RG. Here is what we integrate: exponent h x minus 1/2 of norm of h square, multiply on the density. It is 1 over square root pi d. Here is exponent minus 1/2 norm of x square dx. It can be easily seen that the product of these exponents can be simplified essentially, and we can write finally. The following. It will be equal integral of d 1 square root of pi d power, multiply on the exponent. Here is minus 1/2 norm of x minus h square dx, and it is equal to 1 because here it is written exactly the density of the normal distribution with the mean h and identity covariance matrix. So our random variable e of h has expectation equal to 1. And it is interesting that when we calculate its expectation, it occurs that EH can be interpreted as a density of normal distribution. Excuse me. Here is H. A normal distribution with such parameters with respect to normal distribution with standard parameters. This is a density of one measure with respect to another one. Maybe it is reasonable to give the name to this random variable, and it has the following name. We will say that EH is stochastic exponent. Exponent which is built from H. Okay, so we have such family of random variables, and now let us continue calculations with them. I will now consider L as subspace of RG, subspace of RG, such that dimension L is less than D. This is a proper subspace. I will define the sigma field FL as a sigma field generated by the random variables of the type lambda xi, where lambda belongs to N. And finally, let us find conditional expectation of our stochastic exponent, which respects Fl. In order to do this, I will introduce operator of the projection into the subspace L. So let Q be a projection. Of course, I mean orthogonal projection onto L. Then I can say that our vector H, which was used when we viewed stochastic exponent, can be represented as follows. H is equal to Q of H plus, I will say, H prime, where H prime is orthogonal to our space. Relatively to such representation, one can transform this stochastic exponent. Namely, I can write E of H is equal to E of QH plus H prime. And then it's easy to check due to orthogonality that now I have the following. This is exponent of QL H multiplied on the exponent of H prime. Only what we need to check that the norm of H in square is equal to the norm of H QL square and H prime square. This is just Pythagoras theorem. So we have such an expression. Now let me recall you that we have a standard Gaussian vector and its covariance matrix is identity. So if I take any y which belongs to L and consider the expectation of the product of such two variables, y xi, and here is H prime xi, it will be equal to y H prime because of the covariance of the vector xi is identity, and is equal to 0 because we have such a decomposition of the initial vector H. By the way, these two jointly Gaussian random variables have 0 mean, so here is its covariance. It is equal to 0. It follows that they are independent. Since y is arbitrary, one can say that now our random variable h prime psi is independent from f. Because of expression, I can say exactly the same about this guy. It is also independent from the sigma field Fl. From other side, this one is measured. So finally, I can say that we split our stochastic exponent into the product of two stochastic exponents, where one is independent and another one is measured with respect to FL. Due to this, when I will calculate conditional expectation with respect to FL, what I will get? Like I will take one of these exponents out of expectation and take an expectation of another. So finally, a conditional expectation of our stochastic exponent EH with respect to sigma fields L can be expressed as stochastic exponent of Q and H multiply on the conditional expectation of E H prime FL, which is equal to simply expectation because of independency. So we have this one, QL H, and here we have the expectation of another exponent related to the vector H prime. And we already proved that it is equal to 1. So finally, we get the following nice formula about the conditional expectation of the stochastic exponent with respect to sigma field generated by the linear subspace of our RV. So finally, conditional expectation of exponent EH with respect to FL is equal to stochastic exponent based on the projection of our initial vector H in our subspace L. So we have such a nice property for stochastic exponents. It leads to interesting conclusions, which I will do, which I will show you just taking derivative of stochastic exponent. What I mean by derivatives of stochastic exponent. Let us write again stochastic exponent related to the vector H in the coordinate form. It will be like exponent sum from k equal 1 to d hk psi k are coordinates of our vector h, coordinates of our vector psi, minus 1/2 of the sum of k equal 1 to n hk square. So we have such representation, and now one can take the derivatives with respect to hk of this derivatives with respect to hk of this expression. So let us do this. What we will do? We will consider the Taylor expansion of this function. But in order to simplify, by the way, here is d. In order to simplify our considerations, let me start from the case d equal to 1. Then we will have exactly the following case. We will have exponent of h psi minus 1/2 of h squared. Let me try to find its representation as a Taylor series with respect to h. It is a good function, so one can conclude that it must have Taylor expansion with respect to h. It occurs to be true. And here is the following. It is 1 over k. Here is h in k power, and here is some polynomial hk. What is this hk of psi? hk of let me write now, not random value, but number x can be obtained by the following formula. It is minus 1 in k power e x squared over 2, and here is d dx k in k power applied to minus x squared. Yeah. Let us check that this relation holds. To do this, it is convenient, instead of this expression, to work with the following exponent. Here is minus 1/2, and here is psi minus h squared. This function now can be interpreted as a function e minus 1/2 of x squared at the point psi perturbed by the shift on minus h. So it must be equal to sum from k equals 0 to infinity. I am writing the Taylor series minus h in k power k squared. And here, what I have to write? I have to write the dx k e minus x squared, and when x is equal to psi. Yeah. So when comparing these two expressions, one can, together with this formula, one can understand that here we have exactly the polynomial of this kind. These polynomials are very famous and has the name Hermite polynomials. So I will refer in the future on HK as a Hermite polynomial of order K. We have such an expression for stochastic exponent, and from this expression, I suppose to get some properties of Hermite polynomials. First of all, let me prove the lemma that Hermite polynomials occurs to be orthogonal. Namely, if we take conditional, if we take expectation of h n psi and h m psi, it occurs to be n factorial multiplied on the Kronecker symbol delta nm. Delta nm. So it is equal to 1 if n equal n m, and 0 in opposite case. We have such a relation, and let us check it.
Sorry, I missed what is smaller, n or m?
You see, here we have the index of the Hermite polynomial, and from this expression, it can be seen that k is not only formal index. This is a number of the derivative, which represents this polynomial, and moreover, it is a degree of this polynomial.
Yes, but in the lemma, in the statement of the lemma, what is smaller, n or m?
N and m are indexes, and here is n also. So for arbitrary indexes,
Okay, yeah. Sorry.
we have such a relation. Let's prove it. Let us prove it. So what I have to do, let me consider n which is less or equal to m. This expectation of hn psi multiplied on hm psi is equal to the following integral. I have to It is equal to 1 over square root of here is integral over r. Let me write these expressions in terms of the function of the derivative. So we will get x equal to here is minus 1 in power. Here is dx and e minus x order multiply on the same expression for hm e x order. Here is minus m dx m e minus x and multiply e minus x square dx. So what we have, we can cancel one of these terms, and let me do it here. Let me do it here. Okay. Then see what remains. We have the derivative of this function multiplied on some polynomial. Let me recall you that this is polynomial of degree n, which is less or equal than n. So what I'm doing now? I will just use the integration by part formula a lot of times. It is very convenient to do this now. Why? Because this function, together with its derivatives, decreases on the infinity rapidly than any polynomial. So the terms which arise in the integration by part formula not related to integral, the terms with differences are disappeared. So we have only new integrals, and see what happens. We will change the sign, so we will have like minus 1 in n plus n, minus 1, minus 2, and so on. And then also we will fill the degrees of this polynomial, yes, because we will take its derivative. And we have two possibilities. Either if m is greater than n, strictly greater, then we finally kill the polynomial and get 0. Yeah. In opposite case, we will have just one exponent. We will leave just one exponent there, and we will have the derivative of this polynomial, which coincides with its degree. But I think that you can easily get by mathematical induction that Hn has the following form. Hn of x has the form xn plus something. So the term with the greatest power has the following form. Due to this, we get after n time taking derivative, we get n factorial. So it is equal exactly what we need. It's equal to n factorial multiply over delta n. The lemma easily follows from the application of integration by part formula m times. It is interesting result because it says us that our Hermite polynomials are orthogonal with respect to standard Gaussian distribution. Let me write it again. One can check that hk psi k is greater or equal than 0 is orthogonal system. Orthogonal system. Here's the question arises. Is it a basis?
We consider h from psi or from x? Random.
From psi.
Already
and,
random variable.
Yeah, from the random variable, and I mean the basis in the space A2 of all random variables integrate measured with respect to psi. So this is the question. And to answer this question, we have to do some investigation related to the density of polynomials with respect to Gaussian measure. Let us check this statement. So now I am formulating a very important statement. This follows. Let us denote by P1 the density of standard normal distribution on the real line. Now lemma looks like following. Polynomials are dense in P2 are P1x dx. If we will be able to prove this statement, then it will immediately follow from here that our Hermite polynomials are organized orthogonal basis in our space. Let us try to check this. I will begin with the slightly other statement. Namely, I will prove firstly that the set of stochastic exponents is dense in this space. Namely, let us check that the linear combinations of stochastic exponents now they're generated by the real number because we have one-dimensional case of stochastic exponents are dense. I mean, in the same space, and will not write it here. How one can check this? Maybe we can assume that this is a wrong statement and get some contradiction. In opposite case, if our linear combinations of stochastic exponents are not dense in this space, one can find non-trivial function f from here, which is orthogonal to all these stochastic exponents. Let us write this. So in opposite case, we have the function f which belongs to A2 R P1x dx, and f is not totally zero, such that for all A which belong to R, the following integral is zero. Integral with respect to R, f of x, e of a of x, and p1 x dx is equal to 0. Now let us rewrite this integral. We can do this because we remember interesting fact which we mentioned in the beginning of our lecture, that this is a density of the shifted standard normal distribution on the vector A, exactly. So I can rewrite this relation as follows. As follows. For all A which belong to R, we have the following. We just do calculation. Integral fx p1 x minus a dx equal to 0. What is written there? Here one can see convolution of the function f and density p1. Of course, when we say convolution, we have to be precise, because now we can define this convolution in a sense also generalized functions. So let me recall that f is from the space A2 with respect to P1. P1 is rated, is separated from 0 on any interval. So f is locally integrable and can be considered as an element of D star. Exactly the same happened with P1. So one can say that I have the following. It is equal to 0, such a generalized function is equal to 0. But let me recall you that one can take Fourier transform now. And Fourier transform then must be equal to 0. But we already know what is Fourier transform. In another word, characteristic functions of the Gaussian measure. And the most important thing which remains to be true in any space is that characteristic function of Gaussian measure is greater than 0. Due to this, from this one can conclude that this Fourier transform is equal to 0. And finally, this function is 0. But a regular generalized function which is equal to 0 is totally 0. So we have a conclusion that f is totally 0. It is contradiction. Now one can say that stochastic exponent, linear combinations, stochastic exponent, organize a dense family in our space of square integrated functions which respect to standard function. Now let's go further and just recall that when we have the stochastic exponent A, then it is equal to xi minus a square over 2, and then the derivative of the stochastic derivatives of the stochastic exponent with respect to A are exactly Hermite polynomials from psi. So we remember this representation. Here is the sum from k equals 0 to infinity. K factorial hk of xi. So now we know the L2 norm of hk. It is k factorial. Yes. And we know that they are orthogonal. So we know that this series converge in L2 is converge in square mean. Hence, if some alpha is orthogonal to hk side, excuse me, for any k, then it follows. Of course, alpha is measured with respect to psi, we discussed this. Then it follows that alpha is orthogonal to stochastic exponent. Then alpha is orthogonal to stochastic exponent for any a belonging to R, and then we prove it alpha is equal to 0. Now we prove our statement. The polynomial are dense in the space of square integrate functional from standard Gaussian. Here we have a very interesting corollary. It can be formulated as another lemma that for every alpha which belongs to L2 sigma xi, we have a unique representation. Alpha is equal to the sum from k equals 0 to infinity. Here is ak hk of xi. Moreover, this series consists of orthogonal summands, and expectation of alpha is equal a0. Expectation of alpha squared is equal to the sum from k equals 0 to infinity k factorial because of hk ak squared. So we have such nice relation. One can ask, oh, how I can find these coefficients? Because usually when we discuss random variables, what we can obtain from statistical experiments and so on, just some expectations. Yes. So how to find this one? And let me show you very useful relation which allows us to find this coefficient. Namely, let us find this representation. We already know it for E of sum H. It's equal to the sum from k equals 0 to infinity k factorial hk of xi. So the coefficients for stochastic exponent are following. Now let us calculate the expectation of alpha on the stochastic exponent. It can be easily checked that this is exactly the following: ak k factorial h k power. So one can see that this expectation is analytic function, and the coefficients are exactly the derivatives of this analytic function. From this point of view, sometimes it is good to have the name for such transformation, and this transformation tau alpha from A is Ito Wiener transform Ito Wiener transform of alpha. As we have seen, this transform uniquely defined coefficients of the expansion of our random variable with respect to Hermite polynomials from psi. So today we construct Hermite polynomials. We were able to prove that they are dense, that they organize orthogonal basis in the space of square integral functionals from the Gaussian random variable. We discussed stochastic exponent and its properties. Based on this, we know how to find coefficients for expression of any random variable as a series of Hermite polynomials. And next time we will discuss properties of random variables relatively to its representation. And today that's all. Thank you for your attention. Maybe somebody have question or comments, please.
May I ask a question?
Yes.
Is it correct that we have that this hk from xi is just xi minus a divided by 2 and in the power k because of the Taylor formula for the exponent?
No. No. Let me recall you the formula which we used. Let me recall you. This I know why you asking. You see, because here we use the Taylor formula for this function minus 1/2 x minus h squared, and we consider the Taylor formula for this function at the point x with a small perturbation h. And
Yes, but I'm about the another formula, exponent of xi minus a squared divided by 2.
exactly. And you see, let me continue. To better understand it, let me write here xi, and maybe you want here have a. Okay. Then it's equal to the sum from k equal 0 to plus infinity. Here we have ak, k, and here we have minus a, excuse me, minus a because it's minus. And here we have hk of psi. Not hk, excuse me. Here we have d dx k power e minus 1/2 of x squared and x equal to psi. Yeah. So now, how we get Hermite polynomial? Let us multiply this thing onto 1/2 of psi squared. Yes. Then what we will get? We will get exactly the formula. Sum from k equals 0 to infinity, ak, k factorial, hk of psi, just by definition of hk. You see, due to this multiplication, here we just get the expression. Let me rewrite everything here. We just get the expression of stochastic derivative. Stochastic exponent, excuse me. Here's it. You see, you asking because sometimes it is hard to understand with respect to which variable we are considering power series. Now, A is a small perturbation. Yeah? Due to this, HK has a much more complicated structure.
Okay.
This is not a Fourier series for E minus 1/2 of like psi minus a squared, and this is simply the power of psi minus a squared and the series for exponent. This is different case. Okay, another questions, please. If there are no other questions, so see you next week. Bye.
Thank you. Bye.
Thank you. Bye.